Hi, I was asked to share some tips on problem number 6 from this WebAssign. Um, the problem says something like the space station has a mass provided and orbits at a radius above the Earth's surface. Find the gravitational force, find the potential energy, find the weight of the astronaut. Those are the three things that we're looking for. When solving this, some things to consider. One is, did they give you the altitude or the radius from the center of the Earth? I believe in the problem number 6 that we're talking about the radius from the center of the Earth. And that's going to be important because if they give you the radius, and they sometimes do this, or they give you the radius, they say, oh, the space station or whatever is a certain altitude above, you would have to add in the radius of the Earth. And this is the radius from the center of the Earth to the object, right? So all the way to the space station. So that's taking into account this entire distance here. So when we are talking about this problem, question 1 says find the gravitational force. And so to find the gravitational force, we are going to use the equation F is equal to big G m1 m2 over r squared, where m1 is the radius of the space station, m1 is the mass of the space station, which is provided. M2 is the mass of the Earth, which you do have to look up. That would be 5.97 times 10 to the 24th. And then, sorry, 5.98 times 10 to the 24th. And then you would also need the radius, which again is provided. So you can plug that information in to here and get your answer. For part B of this particular problem, you are trying to find the gravitational potential energy. And since we are dealing with a high altitude situation, not just a low altitude, we need to use the fact that gravity is changing. And so when we were talking about gravitational potential energy earlier in the year, we said mgh, but we had assumed that g was constant. The reality is, as you go up in altitude, gravity is dropping. So if we want to take this into account of the fact that gravity has changed drastically, we need to use the equation big G, mass of the Earth, the mass of the space station divided by R. And so again, it's the same data that's up here plugged in down here, and we can get the gravitational potential energy. This should be negative. Remember, we have flipped our sign to say that as we move away from the Earth, the gravitational energy becomes negative. And so we have that negative sign in here. And that could be why some of you may be running into some problems because of the sign that is being used. And again, that's part B. This was part A. Stop the video, look at the equations if you got to this point and these are ones you wanted to work out. In part C of this problem, we need to find the weight of the astronaut. Now, there's a couple ways to do it. And in fact, I did go back in and look over what the textbook authors recommend for this. And they are saying that we should use, and I don't like this idea, that the weight is equal to mass times gravity. And then they have you find G is equal to big G, the mass of the Earth, divided by the radius squared, and then you get an answer and you plug it in here. Great. In reality, all we're doing, and it's just a matter of the way of thinking about it, but it's the same exact thing. This up here was the mass of the astronaut. You really could say big G, the mass of the astronaut, times the mass of the Earth divided by the radius squared. It's just an order of operations thing, but ultimately, force weight can be calculated in this form right here, or it can be calculated in this form. If we do it in the top form, this form here, you'll have to solve for G first. And so when you plug that in, you will get some numbers. If you have any questions, make sure you drop me an email. Your assignments are due later today, but I did want to get this out because I was asked a couple questions.